Greetings, everyone. I'm delighted and honored to give the 2020 Computing and Chemical Engineering Award presentation on a topic that is very close to my heart, which is sustainable design through multi-scale process integration. At present, humanity faces really the grand challenge of sustainability and sustainable development. The symptoms of lack of sustainability are abundant, including freshwater shortage and dwindling natural resources, global climatic changes, environmental pollution, and an increasing rate and ferocity of natural disasters. So an important question to the chemical engineering community is whether we are part of the problem or part of the solution. Another important question that pertains to, especially to the computing and systems technology community, is what is our role in addressing the problem through systems-based concepts, platforms, and tools. So in this presentation, I will try to shed some light on the following questions. How do we integrate sustainability early enough in process design? And can we really identify targets or performance benchmarks before we do the detailed design? And how do we systematically achieve those targets through process synthesis and other systems tools? And also, how do we handle the appropriate level of details at all scales? Since we're dealing with multiple scales here, what will be the appropriate level of details at each scale? So to streamline the presentation, I will first give you an overview of sustainable design through process integration. Then we'll talk about the concept of benchmarking or targeting. And you will see that it's a fascinating concept. And how do we use it to include sustainability in early design? Then we'll talk about industrial symbiosis. And finally, we'll discuss key challenges and future directions. Let's first start with this short video that gives you an overview of sustainable design through process integration. In this short segment, we will discuss sustainable design and process integration. Process design stands on two important pillars: process synthesis and process analysis. Process synthesis deals with putting together the system where we know the inputs and desired outputs, and we're trying to create the system, whether it's a new one or greenfield process or retrofitting of an existing process. On the other hand, in process analysis, we know the inputs and the system configuration, and we're trying to predict the output. The design may be driven by several objectives. An important driver is the need for sustainable development, which includes environmental protection, economic growth, and social progress. From a capital perspective, one can characterize these objectives in terms of the so-called triple bottom line: people, which represents the human capital; planet, which represents the natural capital; and profit, which represents the financial capital. An important attribute of sustainable development is to enhance current growth while remembering that there is a tomorrow and that there are future generations, and that we should be giving future generations the same opportunities to grow and prosper. Therefore, sustainable design involves design activities that lead to economic growth, environmental protection, and social progress for the current generation without compromising the potential of future generations to have an ecosystem which meets their needs. Next, we move to the topic of process integration, which is a holistic approach to process design and operation, which emphasizes the unity of the process, and it optimizes its design and operation. The overarching philosophy of process integration is big picture first, details later. As engineers, we're very successful because we pay attention to details, but sometimes we work on the wrong details. Therefore, it's critically important to first understand the big picture to determine the proper details to be considered. The fascinating thing is that the big picture insights are in no conflict with the subsequent details. This is not just a philosophy, but it is also a working platform, especially through the notion of targeting, which is the identification of performance benchmarks or standards of excellence a priori and ahead of detailed design. This powerful approach of targeting has been a paradigm shift from the conventional learning curve approach, in which we have a number of key performance indicators or KPIs, and over the useful life period of the plant, we keep on having process improvement projects, which for the most part enhance those KPIs, but sometimes they improve certain KPIs while worsening others. And in all cases, we keep on spending money to carry out those projects. Imagine if we have an alternate approach, one where we get the right answer from the beginning so that we can determine the best possible value of the KPI and the minimum cost to achieve it. No learning curve, no trial and error. This is the essence of the targeting approach. Over the past 4 decades, there have been numerous breakthroughs in identifying targets for important classes of design problems, such as identifying minimum heating and cooling utilities through heat integration, optimal combined heat and power or cogeneration, maximum utilization of mass separating agents and minimum cost of external mass separating agents, minimization of water usage and wastewater discharge, optimal management of hydrogen, minimum use of external fresh resources and minimum discharge of waste materials, targeting the performance of distillation networks, targeting the attainable regions of reactors, maximizing process yield, property-based minimization of fresh usage and waste discharge, and maximizing atomic efficiency in industrial symbiosis of multiple plants. Depending on the tracked objectives, process integration has evolved based on 3 categories: energy integration, which started in the 1970s and 80s, mass integration, which started in the late 1980s and early 1990s, and property integration, which started in the late 1990s and early 2000s. Since the inception of these 3 categories, there have been numerous valuable contributions, not only within each category, but also at the interface of more than one category. These contributions paved the way for exciting future research that will contribute to a more sustainable world. So, as the video discussed the important notion of targeting, let me show you an example of targeting. Let's consider the problem of direct recycle. Here we have a number of recyclable streams or sources that we can use in lieu of the fresh streams brought from the outside. The more we recycle, the less fresh we use and the less waste we discharge. The units that can use these streams are referred to as sinks. And each sink has constraints on composition and flow rate of what can be fed to the sink. So the strategies that we have at our disposal, we may segregate streams. That is to avoid their mixing. We may also split the streams and mix the split streams before entering a sink. And what we're trying to determine here is what should go where, so as to minimize the use of external fresh and waste discharge. One approach of solving the problem is to develop an optimization formulation with the objective function of minimizing the use of external fresh or any other objective that we would like to have, subject to a number of constraints that track the segregation, the splitting, the mixing of the sources, the mass balances, flow rates, and composition, while observing the constraints on the different units. and we can formulate the optimization program, and we can solve it for each case we encounter. So that's one approach. Another approach is to derive the optimality conditions so that we can use those optimality conditions every time without having to solve the original optimization formulation. And one way of deriving the optimality condition is through the so-called dynamic programming, or Bellman's principle of optimality. And here it basically implies that an optimal policy has the characteristic that the initial decisions do not interfere with the rest of the decisions to constitute an optimum policy. And if you're interested in the details, you can look up this reference, which is the work with my former students, Dr. Federico Gabriel and Dr. Dustin Harrell. But based on these derivations, then we can actually develop the optimum policy, which can be represented as a graph. In this case, it's referred to as the material recycle pinch diagram. And here we have one curve representing all the sinks, and one curve representing all the sources or recyclable streams. And when they are plotted in a certain way with certain superposition rules, then we get this diagram, which gives us three rigorous targets: minimum fresh usage, maximum recycle, and minimum waste discharge. All of this is determined before we do the detailed design, before we even know what will go where in terms of streams and sinks, but it identifies those targets before we carry out the detailed design. So this is an example of targeting. And as an added bonus, we also get some useful design rules that we can use for creating new designs, or actually for critiquing existing designs. For example, if we want to achieve those targets, we should not pass flow rate through the pinch. That is, the two composites must touch at the pinch. And we should not be using any waste. We should not be discharging any waste below the pinch. Waste should be discharged above the pinch. Conversely, we should be using the fresh only below the pinch, and we should not be using the fresh to feed to any unit that lies above the pinch. Those are insights that we cannot simply obtain by looking at the flow sheet of the plant, but are very visible when we have optimum policies like this. And another point that I'd like to make here, so I showed you an optimization program. We can solve it by algebraic methods or a graph, different ways of looking at the problem and its solution. And depending on your preference and also the type of information you're trying to extract, you have different methods, and they work for different purposes. And by the way, if the streams are characterized by properties, and if the constraints on the sinks are also characterized by properties, then it is possible to develop an analogous material recycle pinch diagram based on properties. And this was the work with my former PhD student, Dr. Vasiliki Kazansi. And you can see here we have a source composite and a sink composite. To satisfy the constraints, we move them in a certain way. And as a result, we get a material recycle property pinch point. And we also determine three targets: minimum fresh, maximum recycle, and minimum waste discharge. Okay, so this was just an example on targeting for the direct recycle problem. A follow-up question is, okay, if we have those targets, in addition to benchmarking the performance, can we also use them to incorporate sustainability in conceptual design? So this is the next topic I will talk about. We'll talk about the use of targeting techniques to incorporate sustainability during the early stage of design. So the common practice is that process improvement projects are largely driven by economic profitability, which is fine. Nothing wrong with high levels of profitability. I often remind people that money and profit are part of sustainability. But if we want to include other sustainability criteria, how do we do that early enough in conceptual design when we still have most of the degrees of freedom for making the main decisions? We should do that, but preferably in a manner that is consistent with how the decision makers make their decisions during conceptual design, which is mostly based on profitability criteria such as return on investment. So let us consider a project P or design P. In addition to the conventional annual economic profit of the project, we have a number of sustainability indicators. Each one of them is characterized by an index I, and each I represents a sustainability indicator such as reduction in carbon footprint, reduction in water usage and discharge, reduction in discharge of certain emissions, reduction in energy usage, and so on. For each one of those metrics, there is a weight, WI, which represents the relative importance of the indicator as a ratio to the economic profit. This weight depends on the company's core values and importance of that metric. For example, if we are in an area with very limited freshwater resources, then the company would assign a high value to the ratio WI. Or if in 1 year, reducing the carbon footprint is a major objective for a company, then that WI will also have to be high. Next, for each one of those indicators, we use targeting techniques to determine the best that we can do. Say maximum reduction in energy, maximum reduction in water usage and discharge, and so on, similar to the example that I showed you before. And so now that we have the benchmark, we can also characterize the impact of this project P on that indicator I. And it is what it is. Sometimes it improves the indicator, in which case it is positive, but still less than the maximum target. It may have no impact on the indicator, in which case it is 0, or it may be negative, that is, this particular project worsens that indicator. And so if we look here, we have WI, which gives us the relative ratio to economic profit. And then we have this fraction, which represents the ratio to the best that the company can do. So here we are comparing the performance of this project to the true potential for that particular process, not for somebody else's. This is the true potential for this particular plant, this particular process. And this ratio may be negative if it worsens the performance, or it may be positive, but still a fraction. And so the product of the two can add or subtract from the annual economic profit, and it will give us an annual sustainability profit. If we divide it by the total capital investment, we get a sustainability weighted return on investment metric, which is analogous to the return on investment. And so the decision makers will have two numbers. We'll have the conventional return on investment, and we'll also have the sustainability weighted return on investment, which has the economic implications and the profitability implications of all the sustainability indicators. And the decision makers are very much used to using this type of indicator, the return on investment, or metric, the return on investment, to make decisions. And therefore, they will look at the two numbers and feel comfortable making a decision based on both. And if the company is true to its core values, if the sustainability weighted return on investment is less than the threshold or the minimum acceptable return on investment, they should not go ahead and implement the project. And conversely, if a project has an attractive return on investment, but its sustainability weighted return on investment is if the company has a return on investment which is less than the threshold value, but its sustainability weighted return on investment is higher than the minimum acceptable return on investment, then the company should go ahead and implement the project. So it gives the decision makers a framework that they are comfortable with in terms of making the decisions. Okay, next I'd like to talk about multiscale and the multiscale nature of systems integration. And as you can see from this Egyptian pyramid, which shows the systems integration should really coordinate all the activity at multiple scales, ranging from atoms and molecules, then going through the unit level, the process level, and then the macroscopic scale. And I would like to illustrate this point using the application of eco-industrial parks, or EIPs. Okay, so what is an EIP or an eco-industrial park? It's a cluster of plants that collaborate by sharing resources and infrastructures. As my former PhD student, Dr. Eva Lovelady, has indicated, an important condition for a successful EIP is that working as collective is greater than working as a standalone facility. So there is something and benefit for each participant. It's a win-win situation. An extended form of mass integration representation that I showed you earlier for direct recycle inside the plant can be used for an EIP, as shown by this representation, developed with Drs. Dennis Spriggs, Ernie Lowe, Jill Watts, and Eva Lovelady. We can use this source, sink, interception, mass integration framework to represent the participating facilities, and the units to be added here referred to as interceptors, and to evolve mass integration techniques to address this multi-scale problem. A special case of an eco-industrial park is referred to as the carbon, hydrogen, oxygen symbiosis network, or chosen for short, which has been introduced by my former student, Dr. Muhammad Nuruddin. Here, the focus is on hydrocarbon processing, and in addition to simply exchanging chemicals, we can actually convert them to other chemicals and to use atomic-based targeting to set the solution for the whole EIP. So let's watch this video and learn a bit more. An eco-industrial park, or EIP, is a community in which organizations cooperate to reduce waste, share resources, and help achieve sustainable development. Instead of operating independently, these plants can exchange mass and energy and create a win-win situation for all participants to improve economic profitability, environmental protection, and social progress. Traditionally, eco-industrial parks have exchanged materials while retaining them in their original chemical form. For instance, when water is exchanged, aqueous streams are collected and treated in a common infrastructure. Then the treated water can be redistributed to the plants in the park. But today, there are new symbiotic opportunities that can be realized if we go beyond the exchange of materials in their original form and instead consider the chemical transformations of the exchanged materials to create value-added or more environmentally benign products. A particularly promising class of eco-industrial parks involves hydrocarbon processing, which is the basis for creating a carbon, hydrogen, oxygen symbiosis network, or CHOSEN for short. A CHOSEN is an integrated group of industrial plants that can exchange mass, primarily hydrocarbons, and energy, and share common infrastructure for the benefit of all participants. In this example, there are several plants that emit wastes such as carbon dioxide, carbon monoxide, methanol, and so on. These wastes can be collected and converted to value-added products such as various hydrocarbons. A very powerful characteristic of CHOSEN is the ability to methodically use targeting techniques at the atomic level to determine performance benchmarks at multiple scales, including the levels of molecules, units, individual plants, an eco-industrial park, and even a region or a state. Here is how the multiscale approach works. First, certain wastes and byproducts are collected from participating plants. These sources are then broken down to their atomic constituents, which allows the tracking of the carbon, hydrogen, and oxygen atoms. Next, reaction pathway synthesis techniques are used to determine the chemistry needed to create value-added chemicals, which are then separated and allocated to industrial facilities within the same eco-industrial park, which are referred to as sinks or sold in the market. Again, a very powerful attribute of this framework is the ability to set rigorous benchmarks for metrics such as minimum waste, maximum utilization, maximum conservation of natural resources, minimum carbon footprint, maximum gross revenue, and so on. These benchmarks can be determined ahead of detailed design and without commitment to the final configuration of the optimum chosen. The net result is a platform for creating novel and integrated strategies with clear and methodical targets and an effective pathway to sustainability. One approach of generating design alternatives for a chosen is shown by this flow chart, which starts with atomic targeting, and then molecular targeting, and then the development of overall stoichiometric relations for the whole chosen, and then reaction pathway synthesis, and then process synthesis of the final configurations. I will not go through the details, but I will just quickly show you an example. And in this example, we have 5 chemical plants that are adjacent to each other. Gas to liquid, ethylene, propane dehydrogenation, methanol to propylene, and vinyl acetate monomer. So at present, each plant operates separately, and the wastes that are discharged are basically not utilized. Now, one possibility is that we can look at collecting those discharged wastes and converting them into value-added products, specifically in this case, to create methanol and acetic acid and make those feedstocks instead of buying them from the market, if there is a case to be made for such a proposition. So I'll show you briefly key results. First, we carry out atomic targeting, and we find out that in order to deliver the required amounts of methanol and acetic acid from the waste streams, we have deficiency in carbon and hydrogen, but we have surplus of oxygen. Then we consider external fresh streams such as natural gas, primarily methane, water, and CO2, and we find out that we need this much of external methane, 2252.25 kilomoles per hour, and we will actually be discharging 1267.5 of water, 449.25 of CO2. Both will be discharged. And those have been determined ahead of detailed designs. Those are rigorous targets. Then we combine the internal and external streams to create an overall stoichiometric equation for the whole chosen. Then we use reaction pathway synthesis to generate the various options that reach those targets. For example, here is an option. It has steam reforming of methane. It has CO2 hydrogenation, and it has methanol synthesis. It has acetic acid from methanol and CO. So we have detailed the building blocks for the chosen. And after we have done all of that, look how much methane is used. It's what we predicted during the targeting. Look how much water is discharged, what we predicted during targeting. And look at how much CO2 is discharged. It's what we predicted during the targeting stage. So here I'd like to emphasize that we have one unique target, but multiple possible implementations. So this is just one implementation. Another possible implementation using, again, reaction pathway synthesis and process synthesis, we get a different option. It has reforming of methane to hydrogen and CO2. In the previous example, in the previous implementation, it was to CO and hydrogen. It has reverse water gas shift reaction. And again, look at the usage of methane, the target. Look at the discharge of water and look at the discharge of CO2. Those are the targets that we calculated upfront. Can continue to do that in many ways. Here is a third option, and this one has dry reforming of methane or natural gas, and so on. So really, we can generate multiple designs that meet the targets. If we add another objective, such as maximum profit or maximum sustainability weighted return on investment, then we wind up with a unique implementation that meets those targets. There are different categories of the chosen problem. As I indicated, it started with the work of my former student, Dr. Muhammad Nuruddin. And here is another paper on a shortcut approach using algebraic equations. One can use disjunctive programming, such as in the work with Dr. Jose Maria Ponce Ortega and his student, Maricruz Juarez Garcia. We can also look at the so-called anchor tenant problem to start the design with two large plants, then invite other plants that would make sense in terms of participation, such as in the work of my former students, Dr. Kevin Topolsky and Dr. Muhammad Nuruddin, in collaboration with Dr. Fredwell Jack. Or we can use chosen as a multi-scale cluster to reduce the carbon footprint for the cluster of the participants, such as in the work of my former students, Dr. Mark Panu, Dr. Kevin Topolsky, and Ms. Sarah Brush. We can also look at the problem of dealing with uncertainty and reliability of the streams. If multiple companies cooperate together, then there must be some assurances of the reliability of the feedstocks, quality and quantity. And so this work with Dr. Rajiv Mukherjee addresses the issue of reliability of chosen under stream uncertainty. In addition to integrating mass, we can also do the integration of energy among the participating plants, such as in the work of Dr. Topolsky, Fernando Lira, and Ponce Ortega. Looking ahead, there are various challenges and opportunities in the field. I will talk about 6 of them. And they will range from intensification to integration with experimental work, lowering carbon footprint, role of renewable energy and carriers of chemicals, process safety, and resilience. Okay, let's start with process intensification, which is naturally aligned with sustainability. So as described in the work of my former student, Dr. Musaad Al-Thubaiti, and with Dr. Jose Maria Ponce Ortega, there are three primary manifestations of intensification: to reduce the size of the plant for a given throughput, or increase the throughput for a given plant size, or to enhance the process performance as a whole, including enhancing profit, enhancing mass intensity, enhancing energy intensity, and so on. And we have seen before, these objectives are really at the very heart of process integration and can be obtained through targeting techniques. And all of these will lead to enhanced sustainability. I also would like to briefly mention a current AICHE rapid project on intensification, in which my colleagues from the Texas A&M Energy Institute, Dr. Devalina Singupta and Dr. Joseph Kwan, and I are collaborating with partners from the University of Texas at Austin, the University of Pittsburgh, and US Clean Water Technology to come up with systematic approaches for deploying intensified, automated, mobile, operable, and novel designs, or DIAMOND for short, to treat shale gas wastewater, which is really a very important environmental problem. And here we're deploying skid-mounted units to treat wastewater while capitalizing on mass, energy, and property integration, and also while developing process design and scheduling techniques for deploying those solutions. Renewable energy is gaining increasing applicability, but so far it did not have a huge share of energy usage in the process industry. This is changing quickly because of the realization that there are very unique opportunities for integrating renewable energy with the processing industries and to create energy and mass carriers that can be distributed globally. For instance, in this patent with my former student, Juliet Campbell, solar energy, water, CO2, and natural gas are collectively used through elaborate mass and energy integration schemes to produce value-added chemicals that can serve as carriers for mass and for energy, and dispatched through chemical supply chains. Another area that is gaining a lot of interest is water energy nexus. There are numerous examples, and here I chose to show you the work of my former student, Dr. Nisreen El-Sayed, with Professor Maria Barufit, on industrial symbiosis through water energy nexus. The first figure here shows a standalone scenario where we have two separate entities, a processing facility and a water treatment plant that uses thermal membrane distillation. In the second figure, then we have a symbiotic relationship between the processing facility and the thermal membrane distillation water treatment network. In this case, we take excess heat, typically low-grade excess heat, and we use it to run the thermal membrane distillation network. And this is a win-win situation because here we reduce the cooling utility for the processing facility, and we reduce the heating utility for the membrane distillation water treatment network. We also use it to treat industrial wastewater and to produce fresh water, which may be used again in the process or sold in the market. This slide is a follow-up on water energy nexus, and it's based on the work of my former student, Dr. Fadel Al-Abusi, which shows even higher levels of integration, including the use of solar energy, both directly and through storage, the use of multiple water treatment technologies that use thermal energy and electric energy, and the incorporation of cogeneration system, which is used to integrate both heat and power, and to link this with the water treatment issues. So we have water energy nexus that includes renewable energy, multiple forms of water treatment systems, the use of electric and thermal energy, and the coordination among all those activities. And that can only be done through an integrated framework. Another important topic for our computing community is that we really need to reach out to our academic and industrial colleagues carrying out experimental work. Process integration can be very nicely integrated with the experimental work by providing benchmarks and guiding insights to the experimental work, while benefiting from tailored experimental data to drive the design. And here I'm showing work in collaboration with my colleague, Professor Nimr El-Bashir, and former and current students, Abdulrahman Sahibani, Sheikh Abzal, and Sufyan Chaliwala, to coordinate the development of developing catalysts and reactors with process synthesis, simulation, and integration. And based on this coordination between experimental work and systems work, new configurations and catalysts have been created. In this case, what is shown here for a methanol process. Another example for successful integration of systems engineering with experimental work is to facilitate the pathway to innovation in the case of lowering the carbon footprint. And again, here, what I'm showing is the work led by my colleague, Professor Nimr El-Bashir, with PhD candidate Sufyan Chaliwala, and our colleague, Dr. Debalina Singh Gupta. And this patent shows how we can monetize CO2 into value-added syngas and also hydrocarbons. Plus, we produce solid carbon that turned out to be in the form of high-value carbon nanotubes. So not only do we get rid of CO2, but we actually create value of chemicals, and in this case, value in terms of carbon nanotubes. And an added benefit is that the solid carbon out of the system helps greatly when we carry out the life cycle analysis because it's not released again into the environment. Next, I'd like to highlight the need to consider process safety, both in conceptual design and also as part of sustainable design. So to help the process designers include safety, metrics must be developed to guide the design. Process engineers always like to have metrics. And here I'm showing you a sustainability and safety weighted return on investment metric, which is more general than the sustainability weighted return on investment metric that I showed you earlier. And this work was led by Professor Arturo Jimenez Gutierrez and his PhD students, Karen Nguyen Cuevas and Paulina Ortiz Espinoza, with collaboration by Professor Nick Kazansi and my former student, Jem Ozinan. And actually for this work, Karen and Paulina received the AICHE's Sustainable Engineering Forum Best Student Paper Award. So again, this is another way of including safety through a metric that the decision makers are comfortable with, which is a return on investment. Of course, there are many other ways of including safety in conceptual design, and I recommend this review paper, which was led by my PhD student, Sanhua Park, where she, in collaboration with Drs. Zhu, Rogers, and Passman, provided a critical review of the various methods and metrics for including inherent safety in conceptual design. Also, as shown by the work of my PhD student, Ahmed Al-Douri, in collaboration with Drs. Kazansi, El-Jack, and the late Professor Mannan, it is also possible to develop an economic framework for including reliability, availability, and maintainability to help process designers include those aspects during conceptual design. Another important area is the use of process integration to develop disaster-resilient designs of industrial processes. In addition to the conventional approach of protecting the physical infrastructures and restoring operations to the normal or original performance, I mean, that is important. But in addition to that, we should also be thinking in a broader way. Sometimes we should accept failure as an outcome of a natural disaster, but then we need to pre-design the system so that it fails safely. And that requires actually thinking early enough during conceptual design or retrofitting to make the design fail safe. Also, another thing that is becoming very important is how do we pre-design the process so that it can be repurposed to produce other chemicals. Suppose that we have a pandemic and we have shortage during the times of the pandemic or other disasters. And it turns out that process integration provides a very powerful framework for creating designs that can be repurposed during pandemics or other disasters to produce the chemicals that we needed to cope with the emerging needs following a disaster. And as shown in this paper with my colleagues, Drs. Singupta, Bistokopoulos, Salmons, El-Jack, and Kazi, there are 12 primary strategies for using process integration to create resilient design. And there are really many more exciting frontiers in the field, and those are to be explored and developed. And I really hope that this presentation inspires researchers and practicing engineers to create opportunities and to develop new concepts and tools for enhancing sustainability through process integration. Before I wrap up the presentation, I would like to make several acknowledgments. Of course, very grateful for all the research funding that I have received from various sources, and also the generous endowments provided by Mr. Artie McFerrin and the McFerrin family, as well as Dr. Jerry Bullen and Bryan Research and Engineering. Those endowments have helped my group explore very exciting topics in the field of sustainable design. I'm truly indebted to Dr. Dennis Spriggs, who taught me the importance of big picture first, details later, and what he coined as the science of the big picture and how to translate it into industrial practice. I'm grateful to Dr. Subhas Sikdar, who taught me many lessons in sustainability and sustainable design. I'm very grateful to my master's thesis advisor, Professor Mahmoud El-Halwagi, who taught me the power of using mathematical modeling and mathematical programming in addressing complex engineering problems, and to also thankful to my PhD advisor, Professor Vasilios Manasiodakis. I'm also very grateful to the numerous supporters, mentors, and friends, especially to Professor Stratos Bistokopoulos, to my academic great-grandfather, Professor George Stephanopoulos, to Professor Ignacio Grossman, to Professor Rakesh Agrawal, to Dr. Gavin Towler. I'm truly grateful for your wonderful support. I would also like to express a great deal of gratitude to the remarkable professors within Texas A&M and also around the world with whom I had the pleasure of collaborating over the years. Many thanks to all of you and to your students and group members as well. Very special thanks and appreciation to the more than 100 graduate students with whom I had the privilege of serving as their advisor. I've been truly fortunate to have the opportunity to work with this remarkable group, and it has been a very rewarding feeling to see all of you grow professionally and make such amazing contributions. I tried in today's presentation to show a small sample of your work. So today's presentation is given on your behalf, and I'm accepting the award on your behalf. Finally, and most importantly, my deepest thanks to my family in every possible way. I'm very grateful to my mother. She has truly been a constant source of love and blessings throughout my life. I'm also grateful to my grandfather, the late Dr. Mahmoud El-Halwagi, for instilling in me a deep love for chemical engineering from a very young age. And I'm truly indebted to my father, the late Dr. Mahmoud El-Halwagi, for his love and support and for being my most profound mentor in chemical engineering and sustainability and in life. I'm thankful to my brother, who has been my lifelong friend and supporter, Dr. Baher El-Halwagi. And I'm very, very grateful to my sons, Omar and Ali, for being the sunshine of my life. They have always made me very proud, not just because of their remarkable achievements, but more importantly, because of the amazing characters they have and their selfless dedication to help many others and to be change agents for a better world. I'm thankful to my daughter-in-law, Doha, who is a true blessing to have, not just in the family, but to the world, especially to the sick and the needy. Finally, words cannot express my gratitude to my wife, Amal, for her constant love and support and for huge heart that she has. Not only is she a top-notch chemical engineer who has always provided me with wonderful engineering insights, but she is also a remarkable partner with superb human qualities. Because of her love, compassion, support, and wisdom, I owe her everything and anything I may have achieved, including today's award. Finally, I would like to leave all of us with this message. For the sake of achieving a sustainable future tomorrow, we all have to act today. Well, thank you very much for your attention, and many thanks to the AICHE CAST division for honoring me with this award. Thank you.